Okay, any question about the content that we had covered in the last class? No questions? Okay, so in the last class, I talked about these four combinations in which you could use IPsec. Okay, so I had talked about that you could use ESP with or without authentication, and you could use those two things, the modes, the methods of the ESP in two modes. So transport mode and tunnel mode. Okay, so here what I'm trying to show you is how do we process an IPv4 packet and how do we process an IPv6 packet. So there is not much difference between those two, and therefore I will go into a little depth while discussing the IPv4 packet, and then IPv6 packet will be a direct extension of what we would have discussed for IPv4. Okay, so IPv4 packet, you see you have an IP header. So in the last class, I showed you that this IPsec comes. So if so this IPsec security is applied to a packet after the IP header is added to the packet. So here we have the IP header, and then you have this TCP header, and then you have the data. So this is the packet that we have to secure using IPsec. Okay, so now we have two modes, transport mode and the tunnel mode. So in the transport mode, what you do is you take the TCP header and you take the data and you encrypt that part. And of course, you have to probably add some other information corresponding to ESP. So for instance, if you have to do padding or anything, all of that comes under the purview of encryption. And then once you have that ciphertext, what you do is you add one ESP header. So this header will contain information about whether you are using authentication or not, or some other information about the ESP mode. And then you go ahead and authenticate the ciphertext along with the ESP header, and then the authentication tag is concatenated with that packet. And then at the end, you add the original IP header back. Okay. So you please note that in the transport mode, the original IP header is neither encrypted nor authenticated. So I think I have repeated it many times, and the reason is that this is very important to note that the IP header is neither encrypted nor authenticated in transport mode. Okay, any question about what happens in the transport mode? So notice that it is the encrypt then authenticate technique of authenticated encryption. So we had discussed that authenticated encryption can be implemented in many different ways, and the most secure or the most so the most flexible, so in terms of what algorithms could be utilized for encryption and what algorithms could be utilized for authentication, is the encrypt then MAC approach. So if you follow the encrypt and MAC approach, then you have a lot of flexibility in what type of encryption algorithm you could utilize and what kind of authentication algorithm you could utilize. And the IPsec utilizes this most secure approach of doing both authentication and encryption. So you go ahead and do encryption first, and then you go ahead and do authentication. Okay, so any question related to the transport mode? Okay. Am I audible?
Yes, sir.
Okay. Okay, so
Yes.
we have now the tunnel mode. Okay, so remember in the last class also I said that tunnel mode now will capture the IP header as well. Okay, so you could see this very clearly here. So you start with this original IP header, TCP header and data, and then you take the whole thing along with some trailing bits, and then you encrypt this whole thing. Okay, so the original IP header is encrypted as well. And then you do very similar thing about authentication. You add a header, ESP header, you authenticate it and add the authentication tag or concatenate the authentication tag with the packet. So now your original IP header is encrypted as well as authenticated. And that is the reason you would see that this word tunnel means that now what you have done is you have created a secure tunnel through which you are sending your packet. Okay, so IP, so this whole packet is now sent through this secure tunnel. And when visualizing about this tunnel, you can think about a secure VPN. So this VPN would be able to establish a secure connection between your laptop and some server, and therefore you could probably visualize when you are visualizing this tunnel as that VPN connection. Okay, and then of course because the IP header is now encrypted, that is not very useful for um, the networking infrastructure, switches, routers. So you have to add some IP header for, so that this packet is directed towards the destination, and then you can, therefore you need to add a new IP header. So we discussed that in the last class as well. Okay, so any question related to what happens with an IPv4 packet in the tunnel mode of ESP? Yes.
Sir, the contents of the original IP header and new IP header are same.
Content from the, no. If it is same, then there is no reason for doing encryption, isn't it? You try to do encryption in order to provide confidentiality to the original IP header. And so if they are the same, it doesn't make any sense. So as I had discussed yesterday, that what are some of the things that could be done using this tunnel mode. So I had said that if you have a source, okay, and then you will create this tunnel, the source will create this tunnel, carry out this tunnel mode for IPsec, and then the packet is actually can be sent to a firewall, and then the firewall, behind the firewall could be many destinations. Okay, so destination D1, D2, D3, D4, D5, D6. Okay, so now this original IP header, let's say, correspond to D3. But what you could do is, in the tunnel mode, when you add this new IP header, this IP header will only correspond to the IP address of this firewall. Okay, so if so now whoever takes a look at the packet while it is being communicated in the tunnel, it will know that this packet is destined for the firewall, but it will not know which is the actual destination of this packet. Okay, so it will not know that this packet is actually going to the D3. So once the packet is received by the firewall, then the firewall will do authentication and decryption. It will extract the original IP header, and then it will direct the firewall will direct the packet to D3. Okay, so that will happen after it has passed through insecure internet. But over the internet, the attackers or any eavesdroppers will know that this packet is going only to that particular firewall. It will not know the destination. Okay.
Sir, is it possible that someone can tamper with the new IP header, like the outermost one?
Yes, it can always happen that this IP header could be tampered with. But the thing is that remember we had this protocol stack. So what we are doing is that we started with some data. We could do some encryption and authentication for using TLS. Then you might have this IPsec at another layer. Then below that you will have link layer where you could have uh, which means either you are using Wi-Fi or Bluetooth or something. So there also you can have some encryption authentication. And so yeah, at physical layer typically we don't have anything, but so you have this layered structure, and if you feel that it is possible that this link layer packets IP address could be tampered with, then on the next layer you could do some processing um, so that at the link layer, which sits below the IP layer, there you could do some authentication in order to prevent such spoofing.
Sir, I suppose some application also encrypts the data. So, is there any incompatibility in both the encryption algorithms at IP level and application level that we need to take care before
No. So
implementing the IP?
typically this layered structure has been designed in such a way that you could process the procedure at each layer independently. Okay, so that is the way this protocol stacks have been defined. You will not find the same or all the layers in a particular implementation. Some layers might be missing in one implementation to make it more lightweight. You could see that all the layers are present in some other implementation. So there is a lot of flexibility in implementing the protocol stack of this networking. And the reason why this flexibility is there, because the procedures at one layer do not depend on the um, do not directly depend on the procedures of the second layer. So typically, if you just think about encryption, so we talked about TLS encryption separately. We are talking about IPsec separately. Although I am not highlighting about the crypto suits and what algorithms are utilized. So in fact, I would also add that we had this webmail, email security. So there also there will be some different type of algorithms that will be utilized for encryption authentication, and all of those could be independently utilized. Okay, so it's just that when you are processing that packet or encrypting that packet at certain layers, it is possible that the size because of the header is now different, and therefore you might need to do some padding in order to make it equal to a block size. So that is something that you will have to do. But other than that, the encryption algorithm in all these different protocols, security protocols could be different. So starting from so you can think of email as the application. So that had one set of algorithms that could be utilized. So crypto suit, probably let's just use the word crypto suit, and that crypto suit is agreed by the handshake for that layer. So if we are just thinking about email, so application layer will have a handshake, and they will agree on what crypto should be utilized at application layer. Then let's come down, and if we have TLS, there will be a handshake for TLS, and then it will be determined what is the crypto suit that will be utilized. Then we come down in the protocol stack, and then we have IPsec. Again, you will see that in the IPsec, there will be a separate handshake algorithm, and a separate crypto suit will be agreed between the sender and the receiver, and then they will utilize those algorithms. So remember that in this layered architecture, you could think of it that one sender is talking to a receiver, but you can also think of it as one layer of the sender is talking to the corresponding layer of the receiver. So application layer of the sender is talking to the application layer of the receiver. Then in this case, IP layer of the sender is talking to the IP layer of the receiver. Okay, so the handshake or whatever we talk about, you can think that the IP layer of the sender is doing the handshake with the IP layer of the receiver. Okay, so all these different layers typically work independently. So of course, there are different implementations to make things lightweight, and but we will stick with the argument that we are looking at a conventional implementation of these layers. Okay. 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 Any other question? Okay. Okay. So for an IPv6 packet, so if you know the context between IPv4, so IPv4 is a traditional way of assigning an IP address to devices, but those addresses are getting exhausted, and therefore we need a larger size address, and IPv4 v6 provides that larger address. So so there is not much difference. It's just that this the length of this overall IPv6 header is longer than the length of the header corresponding to an IPv4 packet or IPv4 header. So it's just a longer header, but the processing will remain the same. So in the transport mode, you have so you do something interesting. You also have this destination IP address, which could be encrypted. You have TCP header and data that is encrypted, and then you have this whole thing along with the ESP header authenticated, and then you put down the original IP header, and also you could put some more information, which such as hop by hop destination routing or similar things. So rather than allowing each networking component to direct the packet, you could actually define how this packet should be processed by each of those networking components. Okay, so that is the transport mode. Again, in the tunnel mode, we put everything along with the TCP header and data, all the total header at the IP layer. We feed this to the encryption algorithm, and the final ciphertext is authenticated, and then new IP header is added, and then corresponding extension is also added. Okay, so is it clear? So it is just a direct extension of what we did in IPv4. Okay. Okay. So this is the figure that I tried to discuss in the last lecture. I was just trying to highlight where the IPsec sits. And now that you have seen where the encryption and authentication are happening, probably now you will be able to relate this figure to the protocol stack in a better way. So in the transport mode, this IPsec sits below the IP layer. So the original IP header is neither encrypted nor authenticated. In the tunnel mode, because this original IP header is encrypted, you need to have another IP layer processing, and you add another IP header. Okay, good. Okay, so now we already have discussed the ways in which IPsec provides confidentiality and authenticity and integrity. So what we are now going to do is we now going to switch gears and see how IPsec also provides anti-replay service. So it also prevents replay attacks. Okay, so any question about how IPsec provides confidentiality, authenticity, integrity? Okay. Okay, so now let's look into how this IPsec prevents replay attack. Okay, So so in each of these packets at different layers, you may or may not have counters. But at IP, if you are using IPsec, you definitely add counters to each packet. Okay, so a sequence number to each packet, and that sequence number actually helps in preventing the replay attack. And the way it can be done is that remember you have so when you actually go ahead and try to generate let's say an authentication tag T using a Mac generation algorithm. Okay, so Mac gen algorithm. And so remember I said that this Mac gen algorithm uh, will have a message as input and a secret key, a symmetric key as input. So with these two inputs, the authentication tag could be generated. Now we have to determine what this message is going to be. So for so in the case of IPsec, and when you are using a counter, so what happens is that so this message is actually it consists of two things. One is the packet content, so which means it could be the TCP header and the data. Okay, so let me just represent that with P packet content. And then we also have a counter. So that message consists of now two things, a counter and the packet content. And then of course we will have a key. Okay. So this now message does not correspond to just the payload, but also the headers and also the counter. And then that is what is utilized to generate the authentication tag. Okay, so now that and okay, so so if you read the literature, this message authentication code that we had defined initially is referred to by different names in different security protocols or in different standards. So somewhere it is called message integrity code, somewhere it is called integrity check value, so ICV. So these are just different terminologies, but it just means an authentication tag. Uh, um, so you will also see this term authentication tag at many places. So it's just that people use these different terms, but they all somehow directly mean a message authentication code. Okay, so this ICV is now so the way so you have, so there are two important things that we need to consider in order to prevent replay attacks is that there are counters or sequence number when we are generating so it is part of the packet, and then we are also authenticating that sequence number along with the payload, along with the packet content. Okay. Okay, so now we have a counter and we have authenticated that counter. Okay, so we know that, okay, the counters could be 1, 2, 3, 4, 5, and we can trust the value of the counter because these are being authenticated. Okay, so now what does the sender do? So it starts with a sequence number 1. Okay, and of course, each time a packet is sent, the counter is incremented. Okay, and if the counter reaches some value, to about 32 minus 1, the counter will be reset. So this number is very, very large. So hopefully you will not reach that number. But with increasing communication speed, it is possible that at someday it is these numbers could also be reached, and then you might have to reset the counter. Okay, so can someone tell me what will happen if the counter is reset? So here reset means that the counter will go back and start from 1. Okay, so you might have sent 1, 2, 3, 4, 5. Let's say it is just 8. Okay, so 8 is the maximum number, and then after 8, resetting means that you start with 1, 2, 3, 4, like that. Okay, so what will happen if that is the case, and is that a bad thing to happen?
Replay attacks become possible if it resets.
Yes, yes, that is true. Can someone like to elaborate on that point?
The system will start rejecting the packets because the other side has already been configured to reject the packets which have the same sequence number. So if the counter is reset and packet comes with the value 1, it will be rejected by the other side automatically.
Mm, no, so the thing is that these numbers are quite large. So when you are actually at the end of that cycle, the receiver would also know that the counter is going to be reset, and the receiver will following this sender's procedure, the receiver will also start to look into this reset value, reset or the new sequence number starting from 1. So in terms of logistics, how the packets will be processed, I don't think there is any problem there.
Can happen in the same connection, or connection will
Yeah, so that is, yeah, so we will come to that. So it will not happen in the same connection. So in any case, this number is typically very, very large, so it does not happen these days. But even if it happens someday, it will not happen in the same connection. So we will talk about it. So connection here in the case of IPsec, it is referred to as security association. So we will say that it will not happen in one security association. So a new security association will be created, but I will get back to security association later. So any other comment by anyone? No comments? Okay, so yes, so it will make the system vulnerable to replay attacks because this authentication tag, if it is typically it is a deterministic way of generating authentication tag, which means that if the value of M and the value of K remain the same T will be generated. Okay, so now even after reset, so at this reset value, when the counter has gotten back to 1, and if the attacker has actually captured a lot of packets, and it knew what was the authentication tag corresponding to the payload which was transmitted when the sequence number started from here in the previous cycle, then the attacker knows the authentication tag, and therefore it will be, and it will be, so because authentication tag is part of the packet, it is concatenated along with the packet, so the attacker will know the authentication tag and it can replay that packet. So that is definitely not good, and it will lead to replay attacks, and therefore, so if this counter is reset, then we must change the key as well. Okay, so that is the point that I wanted to highlight, that if you have to reset your counter, no matter what is the upper limit of the counter, then you must go ahead and uh, regenerate the key or let's just say that you have to use a new key. Okay, so the combination of the um, the counter, the payload, and the key cannot be the same for any two packets. So that will break the security of the system. And so if you know that the payload, you don't have much control over the payload. The payload would be something that could be repeated. Therefore, you have control over the counter, and you have control over what key you can utilize to generate the authentication tag. So if your counter is going to be reset, which means it is going to be reused again. So then you should go ahead and change the key. So that is the point that I wanted to make here. Okay, so now what is the receiver's procedure? Okay, so the receiver does something interesting. So what it does is, so of course, these packets are being communicated on internet, and different packets will probably be routed through different ways. And even if, so you know that when you try to ping, you do not get the same number all the time. So the numbers could be different. So the packets travel through, it is possible the packet travel through different routes to reach the destination. And therefore, although the sender might be sending the packets in the sequence 1, 2, 3, 4, 5, but the receiver might get receive the packet in the sequence something like 2, 1, 5, 4, 3. So something like this. So see, a sequence like this is always possible, that the receiver will receive packets in this sequence. And so that is one thing, that the receiver might receive the packets in different order. And then the second thing is that receiver has to provide this entry replay service. It has to prevent replay attacks as well. So considering both these two aspects, the design that has been utilized for the receiver's procedure in IPsec is as follows. So the receiver considers a window size W. Okay, so let's say this number is just 10. Okay, so so if and so this is so you see these probably squares, small squares here. So you can think of them as counters. So it is just one packets that are being communicated over the channel or being received by the receiver. So let's say that this n is some number, let's say 100. Okay, so now if you have set the window size as W, which means that your window contains packets from 91 to 100. Okay, so that is the window that is covering these packets. So packet number from 91 to 100. Okay, so what will happen with this window size? So now if you receive a packet, let's say 92. Okay, so you will receive that packet, and then you will check whether the packet is authentic or not. And if the packet is authentic, then you will mark it as received. Okay, so here in this case, you will, in the figure, you are trying to gray that box that yes, I have received this packet and this is authentic. Again, then after 92, you might receive probably 96. So you will again mark that or flag it that it is a packet that has been received. Then you can go back and receive probably 94. 96 could have been this, but it is fine. So you get that point that then you could go back and receive 94, and then you will mark it as received as well after authenticating. So within this window, the sequence of the received packets does not matter. You can receive one packet, you can mark received, and then wait for other packets. Okay, so this is how the packets within this window will be processed. Now, if you receive a packet which is less than 91 here, okay, so the packets which are on the left side of the window, so then you will just reject that packet. You are not going to process that packet. And how this is going to help? So the so if you think about it, so the sender is sending these packets to the receiver, and if there are an adversary which is eavesdropping the packets that are sent by the sender, then the adversary will have to first receive the packet, do processing at different layers, and then probably try to replay the packet back to the receiver. And therefore, there will be some delay in replaying the packet. So it cannot be just directly replayed by the attacker. It has to do some processing before replaying. And that will add some delay. And that is the reason why the packets could reach late. So the counter value could be lower, but the packets would reach at a particular time where the counter values from the benign sender are high. So the benign sender is, let's say, sending 92, but the packet 90. Okay, so when it had when the sender had sent packet 90, that packet 90 had gone to the attacker, and then the attacker has replayed it, and therefore after the sender has received this packet 92, the receiver receives this packet 90, which is probably replayed by the attacker, and therefore if because in IPsec the receiver follows this procedure that if the received packets number is outside the range of the window on the left hand side here or the lower side here, then you are going to reject it, and that is how you will prevent the replay attacks. Okay, so any question related to how you process the packets if you receive a packet within the window, and how you process the packet when you receive a packet on the left side of the window? So any question related to these two parts?
Sir, at max only 10 packets can be out of order. 11th packet cannot be out of order at any moment in time.
So I'm going to talk about what will happen if you get a packet on the right side. So you can have, let me just also talk about it, and then probably I will take more questions. So if your window is from 91 to 100, and you have already set the parameter of the window size is 10. So then if you receive a packet as 105, okay. So if you receive a packet, what is that? So if you receive a packet as 105, okay, this pencil has stopped working. Okay, so if you receive a packet at 105, then you move the window such a way that now you will be covering packets from 96 to 105. Okay, so because this packet 105 has reached, then you are going to expect, the receiver is going to expect that it will be receiving the packets 104 or 103 very soon, and therefore the window is moved to 96 to 105. Okay, so if you receive a packet on the right side of this window, then you move the window to the right. Okay, and then because now you have moved the window to the right after receiving 105, then even the packets like 93, the packet counter, a packet with a counter as 93 will be rejected. Okay, because the window has moved. Okay, so now that I have explained all three parts within the window, left side of the window, right side of the window, now I think I can take some questions.
Also, this means that the system is configured in such a way that at max 10, if more than 10 packets are coming out of order, then it can be assumed that there was something definitely wrong with the 11th packet which was coming out of order.
Yes, yes, you can put it like that. Okay, yeah, you can put it like that.
And sir, like now since we have assumed that at max 10 packets will come out of order, so now like in this system we saw that 105th packet came and 93 packet was left. Okay, so essentially like when let's say suppose 91 came, 92 came, 94 came, 95 came, 96 came, and then 105th came. So the distance between 96th and 105th one was less than 10. Okay, but then 93 was also missing, and the distance between 93 and 96 is also less than 10. So in that case, 93 is rejected, sir.
Yes, so you do not worry about the distance between packets. You are only while deciding whether to move the window or not, you are deciding on the count value of the the packet with the largest counter value. So that is the only criteria to move the window, you do not worry about what is the distance between two packets, counter values or other things.
Right, sir. Sir, and now since 93 packet is rejected, so this will never come back again.
No, so this is at the IP layer. Okay. So, so what happens is that as we have been saying that the different layers have different services. They provide different things. So at the IP layer, this packet will be rejected. So 93 counter will be rejected. So now so it is now, remember, it is now the receiver. So at the network layer, so the IP layer, so this 93 got rejected. So then it will go to the transport layer. And if you are using TCP at the transport layer, and above that is the application layer. Okay, so the application layer sits at the top in the receiver. So at the TCP layer, that layer will detect that one packet has been dropped because of certain processing or for some reason, and then that layer will make sure that let's request the sender to send that packet again. So that is the job of the TCP, to make sure that it gets back the 93 if the real 93 or the benign 93 count packet is actually dropped. So that is the job of another layer. So the job of it is not the job of the IP layer.
Right, sir. Thank you, sir. Now it's clear, sir.
Sir, when is the counter starts at 1? I mean, in every session it starts at 1 between the
Yes.
client and the sender.
Yes. Okay. Any other question? Okay. So now, in fact, I have to quickly go through a few things because we don't have a lot of time. Okay. So now this is a very high level view of the IPsec between two entities. So let's say again the sender and the receiver. Okay, so we have to do encryption authentication in IPsec. So we have to use a symmetric key. Now, how do you agree on symmetric keys? You have to use asymmetric keys. And asymmetric keys to do what? To do key exchange. Okay, so as part of IPsec, we have something called Internet Key Exchange. And this V2 just means version 2. So these things keep getting updated. So this IPsec V3 means version 3. So the different versions. Okay. So so you see three important parts at the sender and the corresponding three parts at the receiver. So one is the IKE, Internet Key Exchange. Then the second is Security Association Database, SAD, and the Security Policy Database, SPD. And the same things on the receiver side. Okay, so the job of Internet Key Exchange is very clear. It has to do the handshake. Okay, and it has to decide on what crypto algorithms will be utilized between the sender and the receiver. And then it has to utilize asymmetric key, or let's say some key exchange methodology, secure key exchange methodology, to agree on symmetric keys. And then so okay, so now I also want to highlight here one important thing, that in IPsec what we do is so the sender, so remember that in order to provide this replay service, you have to have a counter of how many packets you have transmitted, and then you have to reset that counter, and or you have to change your key based on that counter value as well. So therefore we utilize one symmetric key for encrypting and authenticating packets going from sender to the receiver, so let's say K1, and then other symmetric key for packets coming back from receiver to the sender. So two symmetric keys are utilized in two directions. Okay, so in previous versions, we saw that when we had a symmetric key agreed between the sender and the receiver, we said that both of them could utilize the same symmetric key to send messages to each other. But here in IPsec, we have two different keys for two directions. And one of the important reasons is that this IPsec has to also provide anti-replay service where you have these counters going on. And if both of them are utilizing the same key, you will lose track of how many packets each of them have already sent using the same key. And therefore, the key is unique to one of the entities. Okay, so when they are using one key in one direction, what we say is, in the terminology of IPsec, is that the sender establishes a security association with the receiver using K1. And then we say that the receiver creates another second security association with the sender using K2. So these security associations, SA, they always come in pairs. So the sender creates one security association, which means it will be using K1, and the receiver creates another security association, which means it will be using K2. And both K1 and K2, remember, these are still symmetric keys, and they have to be agreed using the same key exchange protocol. For instance, Diffie-Hellman key exchange protocol. Okay, so so any question related to the security association and internet key exchange protocol? So I will talk about SAD and SPD in a minute. The reason why we have this security association pair. Okay, so now that you have a security association, okay, which means the sender knows what key it will utilize to encrypt and authenticate packet going to the receiver. What it needs to do is it needs to make some decisions. So we saw that we have so many options in IPsec. We could utilize transport mode, we could utilize tunnel mode, we could have encryption in ESP mode, or we could have encryption and authentication in ESP mode. And in some cases, you might also want to just use the older authentication header method of IPsec as well. So you have so many options. And then your sender needs to decide what option to utilize for a particular packet. And therefore, this security policy database is the one which decides this for each packet, that what is it that we should be using for this particular packet. Should we use authentication in ESP mode, or we just encryption is fine for the ESP mode? Okay, so that is one part. Then this security policy is a database, security policy database law. So I will go into a depth a little bit more in a minute. But then you also have you also need to know what crypto algorithms you are using for that security association. So for instance, are you using elliptic curve based Diffie-Hellman key exchange, or are you using RSA based Diffie-Hellman signatures? Are you using AES in counter mode? Are you using AES in CBC mode? So all that information is part of the security association database. So security association, and what are the things related to that security association. Okay, so these are the two different roles that are played by the security policy database and security association database. So if you have questions, just hold on to that, because I will cover that again in a minute. These two things again I will cover in a minute. Okay, so internet key exchange IKE that I showed you in the previous slide. So it utilizes key, does the key exchange for the IPsec. And we have already discussed this multiple times, that the basic Diffie-Hellman key exchange is not secure. Can somebody quickly tell me why it is not secure? The basic Diffie-Hellman key exchange. If you remember what different key exchange is.
Authentication is missing, sir.
Yes, authentication is missing. So you have to do authentication, and therefore some refinements need to be done in that defilement key exchange. And those refinements we have discussed what to do in order to make the exchange secure. So you could add some nonces, you could utilize public encryption, you could utilize authentication using digital signatures. And that is how you make IKE secure. Okay, so now security association database. Okay, so again, security association is a one-way relationship. So that is important to notice that it is just one-way relationship. So they always come in pairs. So the sender and the receiver will establish two security associations in order to communicate packets among themselves. And what will be the part of the security association database, which means that what are the features for a security association? So the different authentication algorithms that could be utilized and the corresponding keys, the encryption algorithm and the keys, the lifetime of the security association. Yeah, so this is something new. So the security association cannot be just for infinite time. It has to be defined for a certain amount of time, and that is also a parameter that could be defined here. Whether you want to have that security association just for 1 second or 1 hour, that is also something that has to be defined. Then some other properties can also be defined here. For instance, what is the mode, tunnel or transport mode, and anti-replay service parameters. So one parameter I already showed you. What is the window length? So that itself is a parameter, isn't it? I selected 10, but if I select 100, what will happen? There will be different trade-offs that can happen based on how much resistance you have for replay attack and how much packets are being dropped. So based on that trade-off, you decide on certain parameters. So that information is also part of the security association database. And then if you look at the security policy database, as I said that different packets will be processed differently. So if you so this is so all that information in the columns on the left side of this line are the properties of that packet. Okay, so you see that for a particular packet, you might be utilizing UDP. Then your local IP address is this, and you are using this port, and there is no remote IP address. So you are sending this to port 500. So the action that this IPsec has to do is just bypass. This is something that is you are not going to encrypt or authenticate that packet. Okay, so you will just let that packet bypass, and that is what this action means. So in this database, we are putting this information that if this is what happens, then you do this. So if you have a TCP packet going to remote IP 1.4, 1.2.4.10 on port number 80, then you protect this packet using ESP in transport mode. Okay, so you do this procedure for this type of packet. Again, for another type of packet going to port 443, you just bypass that packet. You don't utilize IPsec for that packet. So all such information which are packet dependent, they are part of security policy database. Okay, so I hope that now it is clear what is part of the security association database and what is part of the security policy database. So now let me get back to that figure and see if you have any questions related to these different components in IPsec.
So this security policy database looks more like a firewall rules.
Yes, so the entries you saw that looks more like a firewall type, but it is different. So here you are making decisions. The action options are like you want to encrypt, you want to encrypt and authenticate, you want to bypass, you want to use transport mode, you want to use tunnel mode. So these are the different options. In firewall, you don't have these options. You either allow, disallow, these kind of things, very simple things you do in firewall. So the database looks similar, but The options here are different. The action items are different.
Sir, like every IP header should have a origin and destination address. So in the table which we just saw, for some of the columns, destination IP address was missing. Um,
No, so the thing is that in many cases you are generating packets which will be processed locally as well. So in many cases you are not sending those packets to the networking infrastructure. So if those packets are not going to go to the networking infrastructure, you probably do not need the destination address for that packet. So only if those packets are going to be processed by router switches, then you need a destination IP address. If those packets will get processed locally, then it is fine.
right, sir. And are these actions also based upon the fact that packet is being sent to the same network or outside the network?
Yes, yeah. So you will definitely like to use tunnel mode for providing higher security to your packets when you are sending it over the internet, so outside your network. But if you are communicating within your network, probably you would not use IPsec, or even if you use, you can just go ahead and do only transport mode. That is also fine. So yeah, all these options will depend what is your remote IP.
Right, sir. Thank you, sir.
Okay, any other question? Okay, good. So we will meet again on Friday with a new topic. Okay, so we are done with IPsec here, and you should look for the assignment 3. We are trying to complete it soon. We will try to release it as soon as we could. Okay. Okay, so see you on Friday then. Bye bye.